Welcome to a brief overview of Kepler's laws. So what are Kepler's laws? Kepler's first law, also known as the law of orbits, states that every planet moves along an ellipse with the sun located at one of the two foci of the ellipse, where foci is defined in the next slide. Kepler's second law, also known as the law of areas, states that a planet sweeps out equal areas over constant intervals of time, indicating that areal velocity, which is area over time, is constant. Kepler's third law, also known as the law of periods, is a ratio stating that the period of one planet squared divided by the period of the same planet, the radius of the same planet cubed, is equal to the ratio of the other planets. So Kepler's first law, more in depthly, let's start off with some vocabulary. So an ellipse is the shapes that you can see in these three oval things on here, which is a curved shape that resembles a flattened circle, kind of an oval, which is defined where two foci, such as the sum of the distances from any point on the ellipse to the two foci, is constant. Here you can see I labeled a diagram in the upper left or upper right, labeling the foci and the ellipse, where the foci are points that define an ellipse residing on the major axis. So specifically, Kepler's first law is that planets orbit around the sun with the path of an ellipse rather than in a perfect circle. And the sun is one of the main foci while the other one is imaginary. And it's not necessarily imaginary, it's just there is no defined, it is not defined by a planet. And you can see this in some of the diagrams down here. Additionally, this equation is how you solve for an ellipse. It is also used to solve for a circle, a parabola, and a hyperbola, which are shown in this cone diagram. But Kepler uses ellipses as a method to describe the orbit of celestial bodies around the masses located at one of the foci, which are often the sun, and he does this in his first law. Howman transfer, just briefly, is related to Kepler's first law, and he works to do this by, he explains that when two circular orbits transfer, it happens along an ellipse, which the intercepts of the orbits, which you can kind of see in this diagram in the lower right side, which allows you to do stuff with the semi-major axis and the total energy, but this just allows you to see how ellipses interact with other systems. Now focusing on Kepler's second law, which is when a planet sweeps out equal areas in equal times, meaning that the areal velocity represented by the area divided by the time is constant, whereas angular momentum is also constant, therefore areal velocity must also be constant. And here we have the equation for areal velocity, which is the change in area over the change in time, which is equal to the angular momentum divided by 2m. And then if we look at this diagram here, we can see that the area of A1 is equal to the area of A2, which is equal to the area of A3. And this is because the time it takes to travel between the points is equivalent. And that happens because planets that are closer to the central mass, in this case the sun, experience a higher gravitational pull, causing them to move with a greater velocity at regions closer to the mass. And a bit more mathematical of an explanation to the can be seen with the conservation of angular momentum. So Kepler's second law is actually a consequence of the conservation of momentum, which is true for all systems that only have radial forces. Using the definition of angular momentum, we can acknowledge the existing position vector, which allows us to solve for area. So if we do that, we can look at this cross product right here. And that allows us to look at the vector shown in the triangle I have over here. Where from that we can solve using the cross product of this rule, where we know that this here is going to be equal to 0 because the vectors are parallel to one another, while this we can rewrite over here because we know that it simplifies because gravitational force only applies radially and not perpendicularly, and that makes the angular momentum constant. Now, once we do this, we need to further find the areal velocity and to confirm this law, we must solve for the area using the equation below. And this equation we can find is derived because the area of a triangle we know is 1/2 base times height, where this would be your base and this would be representative of your height, which you can solve by creating a right triangle as shown here. And then you just further simplify it until you get to this down here, which looks very similar to Kepler's second law.
To orbit a central mass, a planet at a fixed distance from the mass must move at a specific speed. Moving too fast will cause the planet to move away from the central mass. We can see here that if the planet is moving too fast, the component of its tangential acceleration opposite to the pull of gravity will overpower the force of gravity. Meanwhile, moving too slow will make the planet move towards the central mass, as the pull of gravity will not be properly counteracted, as seen here. The speed at which a planet can orbit a mass is proportional to how far away it is from the mass. The further a planet is from the central object, the weaker the force of gravity will be between the two bodies. This proportionality is the focus of Kepler's third law. Kepler's third law states that the square of a planet's orbital period is directly proportional to the cube of its semi-major axis. An orbital period is the time it takes a planet to complete one full revolution along an orbital path. And the semi-major axis is the longest radius of the ellipse from the center to the orbital path. With these understandings in mind, Kepler's third law can be simplified to indicate that the time it takes a planet to orbit a central mass is proportional to the planet's distance from that mass. Kepler's third law shows that the time it takes a planet to complete one full revolution, or its period, squared, divided by the semi-major axis of that planet's orbital, cubed, is constant for all objects orbiting the same central mass. This means that the period of Earth, squared, divided by the semi-major axis of Earth's orbit, cubed, is equal to that of, say, Pluto's period, squared, divided by the radius of its semi-major axis. When this calculation is performed with any object orbiting a single central mass, the resulting number will be constant for all objects. Kepler's third law shows that this ratio only relies on one variable, which is the mass of the central body being orbited. This means that if an object can be observed orbiting some central mass, and the period and semi-major axis of the orbiting object can be measured, then the mass of that central body can be calculated. This allows us to calculate the mass of bodies like the Sun and other massive celestial bodies. Kepler's first law describes the physical behavior of objects subject to gravitational forces and helps to describe the motion of these objects. Kepler's first law also indicates the constant conversion of energy between potential and kinetic forms as a planet's velocity changes throughout its orbit, while the force of gravity acting on that planet increases and decreases based on distance. Kepler's second law explains the conservation of angular momentum in a generally isolated system, that system being the orbit of a planet around some central mass, and shows that the angular momentum of the planet will be conserved unless acted upon by some net torque. This principle in Kepler's second law largely mirrors Newton's first law, saying that objects in motion will stay in motion unless acted upon by some net force. Lastly, Kepler's third law focuses on the effect of different centripetal forces on orbiting bodies and how the centripetal force acting on a planet affects that planet's orbital velocity. This third law heavily relates to principles of rotational motion and also helps to describe the nature of gravity as a force. So over constant intervals of time, we can see that there are intervals where more distance is being covered and intervals where a shorter distance is being covered. So based on that information, we know that angular velocity is not constant in this system. Based on this information, we can also see that angular velocity is not slowest when it's closest to the sun. We can actually see that it is covering the most distance when it's closest to the sun. So we know that that's not correct. We also know that the force of gravity is going to be constantly acting between the sun and the planet, and that there's not going to be an instant where the force of gravity is not causing the planet to accelerate towards the sun. So we know that that's not correct. And going back, we can see that the angular distance covered in this interval when it's furthest from the sun is smaller than the angular distance covered in this interval when it is closest to the sun. So we can see that angular acceleration is greatest when the planet is actually closest to the sun.
For a quantitative problem, we'll be solving for the amount of days it takes for Venus to lap Earth, given that neither of them are ahead of each other in their initial position, as well as the perihelion and aphelion of the two planets, which I've shown below. Our first step is going to be using Kepler's first law to determine the semi-major axis of each planet. My math is shown below, and that will be in units of kilometers, which we need to then convert to astronomical units. And then, as you can see, the semi-major axis of Earth is roughly 1 astronomical unit, and the semi-major axis of Venus is roughly 0.723 astronomical units. Secondly, we're going to use Kepler's third law to relate each planet's semi-major axis to their periods in terms of their periods. So as you can see here, I have the math for Earth and Venus, and that output is going to be in years. We want days for this question, so I'm going to multiply each of them by 365 and some change to get the amount of days it takes for each planet to make one complete orbit. Because the planets do not revolve at the same rate, we have to relate them in some way. So, we know that when Venus laps Earth, it will have exactly one more revolution than Earth will. Using that, we can make an equation for the revolutions of Earth and an equation for the revolutions of Venus with one added to it. Now that we have those equations, we can just plug in the equation for Earth into the y value of the equation for Venus to solve for the amount of days it will take for Venus to lap Earth exactly. This amount is almost 583 days, which is, I think, 1.6 years, roughly. And then according to NASA, the actual syndonic period, which is the technical term of what we're finding, is 583.92 days, which is very close to the value we solved for. So this went well.